Good day, everyone. I'm Princess Ashlee G. Garcia, and today I present the research study that I have chosen entitled Exploring Potential Mineral Deposits Integrating Airborne Magnetic and Remote Sensing Data in Northeastern Desert, Egypt. Here, the researchers focused on the Fatira region where geophysical and satellite data are combined in order to pinpoint new exploration targets. In this presentation, we'll cover the following. First is the introduction, followed by the research objectives, geological background, methodology, results and discussion, and finally, the conclusion drawn by the researchers. Now, for the introduction, according to the study conducted by Abu Alam and others in the year 2019, the Arabian-Nubian Shield ranks among the world's richest gold provinces. In Egypt's eastern desert alone, over 250 ancient gold sites have been recorded by Clem and others in the year 2001. The Fatira area stands out because it hosts auriferous felsite dikes, granitic contacts, and sheared metavolcanics, which is a prime setting where orogenic and intrusion-related gold systems form. However, according to the study conducted by Redwan and others in the year 2023, they argue that field campaigns here are expensive and time-consuming. This is because thick weathering, rugged hills, and sparse roads make mapping on the ground a challenge. That's why this study tackles this by using magnetic and aster data to narrow down where to explore first and to map the mineralization potential in the area. Now, for the objectives of this research inspired by the gaps noted from several studies, we have first is to map the hydrothermal alteration zones and the structural controls that localize them. The second one is to detect mineralized zone and porphyry intrusions by identifying their geophysical footprints. The third one is to integrate surface or the aster and subsurface, which is the magnetic data, to produce a cohesive exploration map. And finally, is to propose a low-cost scalable model that can be applied to highly weathered basement terrains worldwide. Now, let's proceed to the geological background. The Egyptian Eastern Desert is a part of the northwestern extension of the Arabian-Nubian Shield, a region built mostly from ancient volcanic arcs that formed during the Neoproterozoic era. In the Fatira area, we see felsite dikes cutting through older rocks like metavolcanic and granitoid, which indicates multiple intrusive events. Additionally, the gold in this area isn't just scattered randomly, rather, it's structurally controlled. Specifically, it tends to occur along shear zones within quartz veins and at the boundaries where intrusions meet the surrounding host rocks. Therefore, these structural features serve as key indicators and geologists actively target them when exploring for gold. Now, for the methodology of the researchers used three datasets and three processing techniques. For the datasets, we have airborne magnetic data, TMI or RTP, and wherein TMI stands for total magnetic intensity while RTP stands for reduced to pole, in order to image subsurface structures. And the second one is the ASTER remote sensing for spectral detection of alteration minerals. And the third one is SRTM DEM to extract topographic lineaments. Moreover, the processing chain included in the research are CET porphyry and CET grid analysis on magnetic data to highlight faults and intrusions. The second one is band ratios and constrained energy minimization or the CEM on ASTER to map alteration. And lastly, we have the DEM based lineament analysis to delineate fracture trends. Now, let's proceed to the results and discussion of the research. According to the study, magnetic data processed using RTP and CET filters revealed major structural breaks, especially in the western and central parts of the Fatira area. These breaks are interpreted as faults and possible hidden intrusions beneath the surface, which are often linked to mineralization. On the surface, Aster remote sensing data, specifically band ratios like 6/7, 6/5, and 4/2, highlighted zones of hydrothermal alteration, especially in felsitic rock units. These are key indicators of mineral-rich fluids moving through the rock. In addition, digital elevation model or the DEM analysis showed that the region's main lineaments or geological fractures follow a northeast to southwest trend. Interestingly, these lineaments intersect directly with both the magnetic anomalies and the alteration zones, suggesting strong structural control on mineralization. Next in the results and discussion, as the researchers overlaid all datasets, several promising zones stood out. What's exciting here is that these newly identified areas closely match with places where gold and quartz veins have already been reported. This confirms that the integrated method not only captures deep geological structures but also detects surface changes related to hydrothermal activity. Together, this helps in spotting potential mineral targets that might be hidden or too subtle to detect with just one method. Additionally, this approach is both efficient and cost effective. It reduces the need for expensive and time consuming fieldwork by focusing exploration on the most promising areas, especially valuable in underexplored, heavily weathered basement terrains like the Fatira. So, by looking at the results obtained by the researchers, we can say that by combining deep or the magnetic and surface, like the aster indicators, we can reduce the chance of missing blind targets, which is great. Additionally, for the cost effectiveness, satellite and airborne surveys cover large areas quickly, lowering the field time and expenses. However, there is a spectral ambiguity here since aster band responses can be muted by sand cover or vegetation. Aside from that, some alteration signals can be hidden unless we check them on the ground. Also, the magnetic data's line spacing limits the detection of very narrow dikes or small faults, which means that field geophysics or drilling might still be needed here. For the relevance of this research in geological engineering, the integrated magnetic and aster maps pinpoint structurally controlled alteration zones in Fatira so engineers can plan safer, more efficient boreholes, cut costs, and build more accurate resource models. In conclusion, using both magnetic data and aster images together gives us a much clearer view of the geology beneath Patira, which is something we couldn't get by just using one of those methods. With this integrated approach, the researchers identified several new high potential mineralization targets in the Fatira area, and these targets align both with surface alteration halos and with subsurface faults and intrusions. Moreover, the results show that the combined aster aeromagnetic method is not only effective here but also scalable. This is because it offers a practical pathway for explorers working in other weathered shield terrains around the world, improving efficiency, reducing risk, and guiding more successful drilling campaigns. In short, by uniting surface and subsurface views, we open fresh pathways for mineral discovery in areas that have long been difficult and expensive to explore, just like this study area of this research. And that concludes my presentation for this research paper involving magnetic method in natural resource exploration.